Students, good morning students. This is Arnachalam, Assistant Professor in Chemistry, Bishopur College at Trichy. In this video, we are going to discuss with the potentiometric titrations. And the principle behind in the potentiometric titration is when a metal strip is placed in a solution of its own ion, there are two possibilities or tendencies. Metal atom may dissolve in the solution as positive ions, leaving the electron on the electrode. The another one is metal ion may take up the electrons from electrode and get deposited as a neutral atom. In this way, a potential difference is set up between electrode and the solution. The instrument used to determine the potential difference between the reference and an indicator electrode. These two electrodes form electrochemical cell that are dipped in a solution to be analyzed. So measured potential difference can be used to determine the quantity of analyte in terms of concentration. So specifically, we are going to discuss with the potentiometric estimation of potassium iodide based on the chemical principle of redox titration. So aim of this experiment is to determine the amount of potassium iodide given in the whole of the given solution by potentiometric titration. The principle behind this experiment, when the titration is carried out by taking iodide solution in presence of acid in a beaker and adding a small portion of potassium permanganate from a burette. During the titration, the following reaction is occur. The I minus is converted into I2 and permanganate is converted to Mn2 plus. Here a redox reaction is taking place. If a platinum wire is introduced into a beaker, the redox electrode platinum I2 to I minus is formed. The electrode reaction is given below. I2 gains 2 electron converted into 2 I minus. The electrode potential E depends on the ratio of the concentration of I minus and I2 in analyte solution. From the Nernst equation, the E of cell is equal to E0 cell minus 0.0591 divided by 2 log of I minus squared concentration of I minus divided by concentration of I2. Hence, the titration can be followed by the measuring the potential of the electrode. Therefore, the electrode is known as indicator electrode. The indicator electrode is combined with a reference electrode of constant potential, and the change in the EMF of the resulting solution is measured during the titration. The change of potential is the maximum at the endpoint. We have the following cell before the endpoint, where the right hand side, that is redox, the indicator electrode acts as a reduction electrode, that is I2 converted into I minus, whereas the reference electrode Hg is converted into Hg2Cl2. Where the anodic reaction, the oxidation is taking place, the Hg is converted into Hg22 plus. In the case of cathodic reaction, I2 converted into I minus. The overall cell reaction, based on the overall cell reaction, the EMF of the cell is equal to E0 of cell minus 0.0591 log of I minus square. During the titration, the I minus decreases due to its oxidation into I2 by the acidified KMnO4. Therefore, E0 cell is gradually decreases. After the endpoint, after the consumption of all iodide ion present in the analyte solution, the cell setup is changed. The MnO4 minus converted into Mn2 plus. The excess addition of KMnO4 in presence of acid MnO4 minus converted into Mn2 plus. So now At the end point, the E0 cell value increases sharply due to the sudden change in the cell setup. So the reaction in the new cell is given below. At anode, again the mercury converted into mercurous chloride. At cathode, Mn7 plus converted into Mn2 plus. The overall cell reaction, the oxidation at anode and reduction at the cathode is given as here. The Hg plus Cl minus MnO4 minus converted into Hg2Cl2 and Mn2 plus. So the cell potential developed due to the presence of Mn2 plus and the MnO4 minus. Presence of Mn2 plus and the MnO4 minus. So now when the MnO4 minus increases, the cell potential also is increasing based on the equation. Apparatus required for this experiment are a potentiometer, platinum electrode and a calomel electrode. The glassware required are burette 50 ml, pipette 20 ml, standard measuring flask 100 ml, 2 numbers. Tools needed for this experiments are potassium permanganate, ferrous sulfate, potassium iodide and dilute sulfuric acid. Procedure for this experiment is to fill up the burette with given potassium permanganate up to the 0 mark. Then the standard ferrous sulfate of 0.02 normal is prepared for 100 ml and then rinse the pipette with the distilled water followed by the ferrous sulfate and putting out 20 ml of the standard ferrous sulfate into a 100 ml beaker. Then connect the platinum and the calomel electrode with the potentiometer, then add 20 ml of 4 normal dilute sulfuric acid since the oxidation of potassium iodide taking place in presence of acid. And add 0.2 ml portion of KMnO4 from burette and change in the EMF is recorded. We observe that EMF increases slowly at the beginning and at the end point it increases suddenly. On titration 2, the standard KMnO4 versus given potassium iodide. The given potassium iodide is made up into 100 ml from which pipetted out 20 ml into a beaker. Dilute sulfuric acid 20 ml is added in it and titrated against KMnO4 taken in the burette as before. The EMF changed by the addition of potassium permanganate is noted as before. So observation and calculations. First one is the standardization of KMnO4. The titration between KMnO4 and the standard ferrous sulfate is carried out and the observation is recorded as volume of KMnO4 and the EMF which is displayed in potentiometer. Then delta E change in EMF, delta V change in volume, delta E divided by delta V and average volume of KMnO4 are calculated. From the observation, we have to draw the graph between volume of KMnO4 added and the EMF for the titration 1. From the graph, it is uncertain to find the exact endpoint from the graph. So, we have to draw a derivative graph between the average volume of KMnO4 and delta E divided by delta V. Derivative graph drawn between the average volume of NaOH and delta E divided by delta V. A sharp peak is observed. The corresponding X value is identified from the graph as 3.3 ml. So this is the exact endpoint for the titration between KMnO4 and standard ferrous sulfate, from which we may calculate the strength of potassium permanganate. The second titration is carried out between potassium permanganate and potassium iodide. For each addition of 0.2 ml portion of potassium permanganate, the EMF is changed slowly up to the end point that is up to 3.6 ml. After the addition of 3.8 ml, there will be a sudden change in the EMF, that is 0.532 volt to 0.804 volt. So the endpoint is located in between 3.6 to 3.8 ml. When we plot the graph between volume of KMNO4 versus the potential, we get the sudden change in the EMF is observed, where it is not the exact linearity, otherwise with the slope is not equal to 0. So that's why the exact identification of the endpoint is difficult from this graph. That's why we are moving into the derivative graph as before. From the derivative graph between average volume of KMNO4 and delta E divided by delta V, we are observing a sharp peak in which the corresponding x-axis value is 3.7, from which we may easily calculate the strength of potassium iodide. In the calculation, first we have to prepare a standard ferrous sulfate of exactly 0.02 normal, for which 0.556 gram of salt is dissolved in minimum amount of water and made up into 100 ml standard measuring flask by adding a small amount of dilute sulfuric acid. Then the volume of ferrous sulfate taken for the first titration is 20 ml and the strength of ferrous sulfate is 0.02 normal. The volume of KMNO4 required for this titration is 3.3 ml, from which the strength of KMNO4 is calculated as 0.1212 normal. In the second titration between potassium permanganate and potassium iodide, so the volume of potassium permanganate required to complete oxidation of given potassium iodide is 3.7 ml. It is observed from the second derivative graph. The strength of KMNO4 as already we calculated as 0.1212 normal. The volume of potassium iodide taken for the titration is 20 ml, from which the strength is calculated as 0.0224 normal, from which we may calculate the amount of potassium iodide present in whole of the given solution is 0.37184 gram. Then we may write our result as the amount of potassium iodide present in the whole of the given solution is 0.37184 gram.